Chapter 10, Sample Problem Number 8. 4 objects are placed in a row at the same height near the top of a ramp and are released from rest at the same time. The objects are a 1 kilogram sphere, a 1 kilogram hollow sphere, a 2 kilogram solid sphere, and a 1 kilogram thin hoop. All 4 objects have the same diameter, and the hoop has a width that is 1/4 its diameter. The time it takes the objects to reach the finish line near the bottom of the ramp is recorded. The moment of inertia for an axis passing the center of mass for a solid sphere is 2/5 mr square. Hollow, it's 2/3 mr square, and for a hoop, it is mr square. Rank the 4 objects from fastest time down the ramp to slowest. So the fastest time down the ramp would be the fastest velocity. So let's figure out who's moving fastest at the bottom of the ramp. We're going to do, for each of them, we're going to do an energy balance. I'm going to say the energy at the top equals the energy at the bottom. The energy at the top, of course, is no kinetic energy, plus mgh, where m is the mass and h is how far they up. And at the bottom, we have 1/2 mv square plus 1/2 I omega square plus no gravitational energy at the bottom. But of course, we have that omega is v over r, because really, as we derive several times, v equals r omega. And so we can look at this and say that mgh is 1/2 mv square plus 1/2 I. But notice that every I is some constant times the mass times the radius squared. And then we have velocity over the radius squared. And so we can say all of this will be factored in. We can say, well, we pull out 1/2 mv square, and we're left with 1 plus that constant, where the constant is either 2/5 or it's 1, or it's 2/3. And then we say, well, the m's cancel, so it didn't matter that it was a 1 kilogram or 2 kilogram hollow sphere, meaning automatically we have, before we go any further, we have A equals C for sure. And then we say that v square is gh, which is the same for everybody, over 1 plus k, 1 plus little k. Where here I want to point out little k is I'm just saying that the inertia is some number times mr squared, where that number varies. This is not the spring constant k. It's just a generic constant. So if we look at this, we have for the solid sphere, we're not a good room, but that's all right. For the solid sphere, k equals 2/5. So v equals gh over 7/5 or 5/7 gh. For the hollow sphere, k is 2/3. So v is gh over 5/3 or 3/5 gh. And for the hoop, k is 1, so v is just gh over 2. All right, I think we need another screen for this. Now remember that since this is true at every height, basically the object that has the faster speed at the bottom has the faster speed throughout and therefore gets there earliest. So we really just want to rank this by speeds. And we can see that the solid sphere is faster than the hollow sphere, which is faster than the hoop. So going back to our originals, so we end up with that the solid sphere, which is both A and C, get there before the hollow sphere, which is B, which gets there before the hoop, which is D.